Hi everyone, my name is Jakub Staroń. This is the next episode of MedChem Essentials, scientific seminars devoted to transferring the knowledge related to medicinal chemistry and drug design and development in general. The topic of today's presentation will be solubility with the focus on theory of hydrogen bonds. As you may recall, this chart represents the roadmap for the upcoming series. And with the last presentation, we finished talking about permeability, and now we'll move on to solubility. We'll start with description of different interactions within solution, then strength of hydrogen bonds. Functional group profiles will be topping the presentation. So, first we need to introduce and answer the question, why solubility is important? Because compound molecules must be dissolved to undergo any pharmacological processes, both in vitro, permeation, metabolism by assay target binding, and in vivo, like intestinal absorption. Solubility will be determined by the energetics of the interaction of molecules with themselves in the crystal. This is a schematic representation of the dissolution process. So at the beginning you have a saturated solution with a solid phase, and how strongly those molecules will interact with themselves in the solid phase will affect how well the compounds will be soluble. Next, we have interactions of solvent molecules with themselves in solution, interactions of solid and solvent molecules in solution, solution components, and physical conditions like mixing or temperature. So at the beginning, with this unsaturated solution, there's a higher number of compounds detaching from the solid phase. In a saturated solution, we have equilibrium, the same number of compounds detached and attached to the solid phase. In a supersaturated solution, there is a high concentration of the solid molecules in the solution, and there is a big tension waiting for any factor that will initiate precipitation, and this can happen by, for instance, addition of a seed crystal, which initiates precipitation, and more compounds attach to the solid phase, and the solution comes back to the saturated state. Now, when it comes to the interactions within solution, there are these interactions, they exist in a competition state between solute-solvent interactions in a free state and solute-solute and solvent-solvent interactions in the bound state. Our solute may have hydrogen bond donor and acceptor properties, so it can form these hydrogen bonds with another solid molecule and also with solvent molecule. When it comes to interactions of a solvent, it can also choose between forming this interaction with a solid molecule or with another solvent molecule. And these both equilibria on the left and on the right will affect the solubility process. And this brings us to the theory of hydrogen bonds. So in very simple terms, we have a hydrogen bond donor and acceptor. And we have two parameters, alpha and beta. Alpha will represent hydrogen bond donor strength, and beta will represent hydrogen bond acceptor strength. The higher the both, the stronger is the hydrogen bond donor or acceptor. And depending whether this alpha and beta will be stronger or weaker than alpha and beta of water, this will affect the nature of interactions being formed. If alpha and beta will be stronger than water, then we have a strong interaction. If alpha and beta is weaker than water, we have a weak interaction. When there is a mismatch in quadrant A and D, then these interactions are enthalpically unfavorable and rather not being formed. If you don't understand right now what does it mean enthalpically unfavorable, it's enough for you to know that they are just unfavorable and these are favorable in water. And when it comes to protein-ligand interactions, for strong hydrogen bonds, we have alpha and beta stronger than water, then protein-ligand interactions dominate. If they are lower than alpha and beta of water, then water-water interactions dominate. For quadrants A and D, protein-water and ligand-water interactions dominate. So, from the perspective of solubility, in quadrant B, the ligand will not be solubilized because it will be bound with the protein. For quadrant C, ligand will be bound with itself and water-water interactions will dominate. It will be precipitated. And the compound will be dissolved in quadrant A and D when ligand-water interactions will dominate. And this brings us to functional group interaction profiles. We'll start with DMSO. I took it from the really amazing, fantastic publication by Christopher Hunter published in 2004. I really recommend everyone to take a look into that because it's truly fascinating. On this chart, we have alpha and beta parameters on Y and X axis. Alpha and beta. And these represent the strength of different hydrogen bond donors and hydrogen bond acceptors. And how to read this chart? If the interaction, we have hydrogen bond acceptor and hydrogen bond donor, so here on the crossing we have interaction of both these molecules, these types of molecules, functional groups. And if this is red, it means it is unfavorable. And so interactions between solvent and solute dominate because interaction between those two functional groups is unfavorable. This explains why DMSO is a good solvent for almost everything. That really interactions of a wide range of different hydrogen bond acceptors with different types of hydrogen bond donors is unfavorable between themselves. That is why DMSO will dissolve them. Almost. But as I said, almost all interactions are unfavorable here. Only interactions in the blue zones are favorable. And this is represented by interactions of hydrocarbons. You have hydrocarbon here, hydrocarbon. So hexane will not be miscible with DMSO. And the same comes to interactions of these molecules. Now let's go into water. Water is a very special solvent because its alpha and beta resides almost in the middle of the scale of the strength of hydrogen bond acceptors and donors. And this has very profound consequences for almost everything because certain key interactions are favorable here. For instance, amide interactions, amide interactions. You have amide here and amide here, and this is on the blue, in the blue zone, so this is favorable in water. Another thing that is favorable in water are hydrophobic interactions of hydrocarbons, and this kind of explains certain phenomena like hydrophobic collapse of proteins and protein stability, like structure of secondary structure of proteins like beta sheets, alpha helices. So imagine we have proteins, DNA, membranes, and they are stable because of special properties of water, which concluding that whole life exists because of special properties of water. When I first realized that phenomenon, I was truly stunned and amazed for a couple minutes. How it is perfectly designed that water is this major solvent on Earth, actually, because without water, life will have completely different shape and structure. So, comparing DMSO and water, much big difference between two of them. But how this affects solubility. How we can explain solubility in water? So we described a moment ago that DMSO is a good solvent for almost everything because those interactions are unfavorable in DMSO. And so we can infer from this, in one simplification, that a compound to be soluble in water will need to have unfavorable interactions with itself in water. So on this chart, functional groups found in the compound that we are making with another groups found in the compound will need to be unfavorable here in the red zone, and the interactions with water should be favorable. Couple of strategies to improve solubility will be based on this phenomenon, but we will discuss this on the future presentation. For now, thank you very much for your attention. See you next time. Bye.